Hello students. In this session, let us solve problems on Young's double slit experiment, that is interference of light. First, let me go through equations involved in this experiment. Next, I will take up few problems. After that, let us solve problems appeared in board exams. Let me go through the equations involved in this experiment. Expression for fringe width. Expression for fringe width usually denoted by beta equal to lambda capital D by small d. In few reference books, they mention lambda capital D by A. Okay, where small d is distance between the slits. So these are the two slits, means this is the median, screen, slit A, slit B. Distance between A and B is D. Capital D is distance of the screen from the slits. Okay, capital D. This is small d. Lambda, the wavelength of light used. This is first equation. Second equation. Distance of the bright fringe from the central bright fringe. If these are the fringes on the screen, this is 0th bright, first bright, second bright. What is the distance of second bright from the central means this distance. Let me denote it by xn. So xn equal to n lambda capital D by small d. What is the distance of 10th bright means n equal to 10. What is the distance of 15th bright fringe from the central means n equal to 15. Okay, so here n. Distance of dark fringe from the central bright fringe. xn equal to (2n plus 1) lambda by 2 capital D by small d. Students, please tell every time capital D by small d. If you simply say d by d, so you may get confused when you are solving problems. Okay, it is always better to say capital D by small d. And please bear in mind, capital D is distance of the screen from the slits. So this is the expression for distance of dark fringe from the central. For 10th dark fringe, n should be equal to 9. For 15th dark, you should take n equal to 14. Make sure that this is less by 1 than this. 10th dark means n is 9. 15th dark means n is 14. Suppose if somebody uses 2n minus 1 lambda by 2 capital D by small d, then they have to take 10th dark, n is 10. For 15th dark, n 15. Okay, for this equation they have to take this. If 2n plus 1 is used, then for 10th dark n is 9, 15th dark n is 14, for 4th dark n is 3. In Young's double slit experiment, light of wavelength 400 nanometer is used. So let us collect the data. Lambda is 400 nanometer, which is 410 power minus 7 meter. Is this clear to you? 4 is 4, 2 zeros, 10 power 2, nano is minus 9, and 4 10 power minus 7. 4 10 power minus 7 meter. Distance between screen and the slit is 1.2 meter. That is capital D. 1.2 meter. Small d. Distance between the slits is 0.6 millimeter. 0.6 millimeter. So we have all the terms. First one, calculate the distance of fourth bright fringe from the central bright. Distance of xn equal to n lambda capital D by small d. For fourth bright, n is 4, implies xn equal to 4 lambda capital D by small d. Lambda is 4 10 power minus 7, capital D 1.2, small d is 0.6 milli, equal to this one, this 2, 4 4 16, 2 32, 3.2 10 power minus 7, minus 3 is minus 4, minus 4 10 is minus 3 meter. Students, please check, simplify this and find out this. I might be wrong. Second, distance of sixth dark from the central fringe. Distance of dark fringe from the central bright means xn equal to 2n plus 1 lambda by 2 capital D by small d. For sixth dark, n is 5. If it is 2n plus 1, then n should be 5. If it is 2n minus 1, n is 4. Implies xn equal to 2 5 plus 1 lambda by 2 capital D by small d. 5 to 10 plus 1 11 by 2. 11 by 2 lambda capital D by small d. 11 by 2 lambda is 4 10 power minus 7, capital D 1.2, small d 0.6 milli minus 3, equal to 0.6 into 2, this get cancels with this, 4 into 11, 44, 4.4 10 power minus 7 minus 3 is minus 4, 1 more 10 minus 3 meter. C, the fringe width, beta equal to lambda capital D by small d. Lambda is 4 10 power minus 7, capital D 1.2 meter, small d is 0.6 10 power minus 3. This one, this 2, 4 to 8 10 power minus 4 meter. Students, copy the problem and copy the solution. Before writing the equation, make sure that you write a statement. In Young's double slit experiment, light of wavelength 5600 angstrom is used. Distance between the slits is 0.8 millimeter. Distance of the screen from the slits is 2.4 meter. Lambda is 5600 angstrom. Angstrom is 10 power minus 10. So if I write it as 15.6, then there are 3 zeros here. 1, 2, 3, 10 power minus 10 becomes 10 power minus 7 meter. Small d is 0.8 millimeter distance between the slits, and capital D is 2.4 meter. Okay. Distance between second dark and 12th bright. Distance of bright fringe from the central bright, that is Xn equal to n lambda capital D by small d. For 12th bright fringe, n is 12, implies Xn equal to 12 lambda capital D by small d. Okay. For second dark, distance of dark fringe Xn equal to 2n plus 1 lambda by 2 capital D by small d. For second dark, for second dark fringe, n is 1, n 1 for second dark. Third dark, n is 2. Okay. Therefore, Xn dash equal to 2 into 1 plus 1 lambda by 2 capital D by small d. 2 plus 1 3, 3 by 2, 3 by 2 lambda capital D by small d. This is distance of second dark. Therefore, distance between second dark and 12th bright fringes, let me denote it by x. It is Xn minus 1, Xn dash, not minus 1, Xn dash equal to 12 lambda capital D by small d minus 3 by 2 lambda capital D by small d equal to 12. 3 by 2 is 1.5. 12 minus 1.5 is 10.5 lambda capital D by small d. 10.5 lambda is 5.6 10 power minus 7. Capital D is 2.4 meter by small d is 0.8 millimeter, 10 power minus 3, equal to 1.76 approximately 10 power minus 2 meter. For PU board students, please use calculator and simplify. Okay. Second is fringe width. Fringe width beta equal to lambda capital D by small d. Lambda 5.6 10 power minus 7, capital D 2.4, small d 0.8 millimeter minus 3. It is 16.8 10 power minus 4 meter. Students, if you have not understood this problem, let me explain. Please understand. This is this screen in Young's double slit experiment. Okay, screen is some white sheet, white plane. This is that plane. There are fringes on the plane. The central one, which is on the median, because if there are two slits like this, A and B, this point O is equidistant from A and B. Then this line is called the median. So fringe on the median is always bright, which is called central bright. Central bright fringe. Okay. And these are the fringes. Suppose if this is 12th bright and this is first dark, second dark. Suppose, please understand, suppose this is 12th bright and this is second dark. So first let us find distance of second dark from the central. Next, distance of 12th bright from the central. So difference of these two gives distance between 12th bright and second dark, isn't it? So that is why we are taking the difference of the distances. Distance between 12th bright and 12th dark, second dark means take the difference of these two. This is 12 lambda capital D by small d. For second dark, we got it as 3 by 2 lambda capital D by small d. And difference of these two is 10.5 lambda capital D by small d. So this is what we used when we were solving this problem. Okay. So every time try to visualize like this. It becomes very easy to understand. In Young's double slit experiment, distance of 10th bright from the central bright is 12 millimeter. So distance of 10th bright, it is given as 12 millimeter. Distance between the slits, small d equal to 1.5 millimeter. Wavelength of light, lambda equal to 650 nanometer. Calculate the distance of the screen from the slits, that is capital D. Now distance of 10th bright is mentioned. Distance of 10th bright from the central bright. So let me write. Distance of bright fringe from the central bright, Xn equal to n lambda capital D by small d. For 10th bright fringe, n is 10, implies Xn equal to 10 lambda capital D by small d, or capital D equal to Xn D by 10 lambda. Xn is 12 millimeter, 12 milli minus 3, small d is 1.5 milli, lambda 650 nanometer is 6.5, 10 power minus 7. I have shifted the numbers I have shifted the zeros. Please take care. So it is 6.5 10 power minus 7. Lambda 10 10. Simplify this. It is 2.77 approximately 10 power 0. See here, 10 power minus 3 is minus 6. 10 into 10 power minus 7 is 10 power minus 6. So this get cancels. So it is 10 power 0. So capital D is 2.77 meter. Okay. Next, the distance of fifth dark fringe from the central bright, B. Distance of dark fringe, Xn equal to 2n plus 1 lambda by 2 capital D by small d. For fifth dark, n is 4. Therefore, two 4 plus 1. Four into 2 8 plus 1 9 9 by 2. 9 by 2 lambda capital D by small d. 9 by 2 lambda is 650 6.5 10 power minus 7. Capital D is 2.77. Just now we found out, by small d is 1.5 millimeter. Milli is minus 3, equal to 54 10 power minus 4 meter. This is distance of fifth dark, or 5.4, just shift the decimal, into 10 power minus 3 meter. In Young's double slit experiment, light of wavelength 5000 angstrom, and so lambda equal to 5000 angstrom. 5000 angstrom, which is equivalent to 5 10 power minus 7 meter. Distance between the slits is 2 millimeter. Small d equal to 2 millimeter. Distance of the screen from the slits is, that is capital D, equal to 1 meter. Find the fringe width and also calculate distance of second dark fringe from the central bright. So let us find fringe width. Fringe width, beta equal to lambda capital D by small d. So beta equal to lambda 5 10 power minus 7. Capital D is 1 meter, small d is 2 millimeter. 5 by 2 is 2.5. Minus 3 minus 7 minus 3 is minus 4 meter. So this is beta. Distance of seventh dark fringe. To n plus 1 lambda by 2 capital D by small d. For seventh dark, n equal to 6. Therefore, (6 to 12 plus 1 13). 13 by 2 lambda capital D by small d. But we already calculated lambda d by d, which is nothing but fringe width. 2.5 10 power minus 4 equal to 16.25 10 power minus 4 meter, or 1.625 10 power minus 3 meter. This is 2019th problem. 2018. In Young's double slit experiment, the slits are separated by 0.28 millimeter. That is, small d equal to 0.28 millimeter. Screen is placed at a distance of 1.4 meter. Capital D equal to 1.4 meter. Distance between central bright and fifth dark is central bright. XN equal to 1.35 centimeter. Calculate the wavelength of light used and also find the fringe width. Fringe width with this condition. Okay. Distance of fifth dark. Distance of nth dark fringe is xn equal to 2n plus 1 lambda by 2 capital D by small d. For fifth dark fringe, n is 4, implies xn equal to 2 4 plus 1 lambda by 2 capital D by small d. 4 to 8 plus 1 9, 9 by 2. 9 by 2 lambda capital D by small d. Okay. What we want is the wavelength, or lambda equal to 2d into xn. 2d into xn by 9d, 9 capital D. 2 small d is 0.28 millimeter minus 3. xn is 1.35 centimeter 10 power minus 2. 9 capital D is 1.4. So simplify and take care of the powers. It turns out to be 0.06 into 10 power minus 5, or 6 10 power minus 7. Shift the decimal point, or it is 6000 angstrom. Next, also find the fringe width beta question mark if screen is moved 0.4 meter towards the slit. So capital D, new capital D is 1.4 minus 0.4. These two are the slits. Median, this is the position of the screen. This screen is shifted by 0.4 meter, means the new distance is 1 meter, that is 1.4 minus 0.4. So capital D is 1 meter. Therefore beta equal to lambda capital D dash by small d. Lambda is 6000 angstrom, 610 power minus 7. D dash is 1 meter by small d is 0.28 millimeter. Milli is 10 power minus 3. Students, don't forget this milli, 10 power minus 3. Okay. Simplify this. It turns out to be 2.14 10 power minus 3 meter. In Young's double slit experiment, fringes of certain width are produced on the screen, kept at a distance, certain distance from the slits. Fine. When the screen is moved away from the slits by 0.1 meter, fringe width decreases by 6 10 power minus 5 meter. Okay. It is 2016 board exam problem. It's mentioned beta equal to lambda capital D by small d. Okay. When moved away, screen is moved away means earlier d plus 0.1 meter for the same wavelength, for the same distance between the slits. The fringe width increases because numerator is increased. Fringe width will be beta plus, see, fringe width increases by this distance, 6 10 power minus 5. Now we have to solve these two. The separation between the slits is 1 millimeter. So small d is 1 millimeter. Calculate the wavelength. Now beta is lambda d by d. Beta is lambda capital D by small d. Substitute this in this. Plus 6 10 power minus 5 equal to lambda d by d. Lambda capital D by small d plus lambda 0.1 by small d. Lambda 0.1 by small d. These two get cancels. So lambda equal to 6 10 power minus 5 into small d. 6 10 power minus 5 into small d by 0.1. 6 10 power minus 5. Small d is millimeter minus 3 by 0.1 is 10 power minus 1 equal to 6 minus 5 minus 3 is minus 8, minus 8 by minus 1 is minus 7. So it is lambda 6 10 power minus 7 meter. When you go through the problem, don't panic. According to the given statement, try to write equations and using high school mathematics, try to solve. Okay. In a Young's double slit experiment, distance between the slits is 1 millimeter. Small d equal to 1 millimeter. The fringe width is found to be 0.6 millimeter. Beta equal to 0.6 millimeter. When the screen is moved through distance 0.25 meter away from the plane of the slit, the fringe width becomes, so for this distance is capital D. Okay. Now the screen is moved away by 0.25 meter means new capital D is, that is D dash equal to D plus 0.25. Okay. That time new fringe width is 0.75 millimeter. See, 0.75 millimeter when the screen is moved away. Find the wavelength of light used. So they are asking lambda. Okay. Students, With this data, you can identify that we need beta equal to lambda capital D by small d equation. So consider beta equal to lambda capital D by small d. Next, beta dash equal to lambda capital D dash by small d. This gives 0.6 millimeter minus 3 lambda wanted capital D by small d is 1 millimeter, 10 power minus 3. New fringe width is 0.75 milli, equal to same wavelength, but it is D plus 0.25 by small d is 10 power minus 3. Small d is 10 power minus 3. Now divide one by the other. Here only you can divide, but still 0.6 10 power minus 3 by 0.7 10 power minus 3 equal to lambda capital D by small d. Here lambda capital D plus 0.25 by small d. Lambda by d get cancels. Minus 3 get cancels. 0.6 by 0.7 is 6 by 7. D capital D by D plus 0.25 or cross multiplying 6D plus 6 into 0.25 is 1.5, 7D, or 60 to the other side, 7D minus 60 is D equal to 1.5 meter. But what we want is lambda, so use this. Consider beta equal to lambda capital D by small d, or lambda is beta small d by capital D. Beta is 0.6 millimeter minus 3, small d is millimeter minus 3 by capital D is 1.5. So it is 0.4 10 power minus 6 meter, or lambda equal to 4000 angstrom. Shift zeros appropriately, you'll get 4000 angstrom. Now this is an additional problem. So such problems are seen in preparatory exams in college level. Okay. First understand the problem. A beam of light consisting of two wavelengths, 500 nanometer and 400 nanometer. So lambda 1 is 500 nanometer, lambda 2 is 400 nanometer, is used to obtain interference fringes in Young's double slit experiment. The distance between the slits is 0.3 millimeter. So small d is 0.3 millimeter. No issues. And distance between slits and the screen is 1.5 meter. Capital D is 1.5 meter. Compute the least distance of the point from the central maximum where the bright fringes due to both the wavelengths coincide. Since wavelengths are different, fringe widths are different. This is median, this is the screen. Red color 400 nanometer, wavelength is less than the other, means that results in small fringes, central bright. first bright, second bright, third bright, fourth bright, and so on. Okay. Of course, these two are the slits, A and B. Now, in the same setup, 500 nanometer is also used. Since 500 is greater than 400, fringe width is more. Let me use other color. Instead of writing the fringes on the same line, let me shift. Let me write next to it. Okay, don't get confused. The fringes are one over the other. Now let me draw broader fringes. This is first bright, central bright, first bright, second bright. Now observe, this is overlapping on this. Central should overlap on central, but first is not overlapping on the first, second is not overlapping on the second, but third is overlapping on the second. Instead of third, let me take this as nth bright, and this is mth bright. Okay, so they are asking us to find the least distance where bright fringes of the patterns overlap. Please go through the problem and go through the explanation. We have to find the distance of that point where bright of one overlaps on the bright of the other from the central bright. So here distance of bright matters. So what's the formula for distance of bright? Xn equal to n lambda capital D by small d. So this is the formula. Okay. For lambda 1 equal to 500 nanometer, Xn equal to n lambda capital D by small d. For lambda 2 equal to 400 nanometer, same Xn but mth bright, lambda capital D by small d. Since these two are equal, of course this is lambda 1, lambda 2. Let me equate n lambda 1 capital D by small d equal to m lambda 2 capital D by small d. D by d get cancels. N by m equal to lambda 2 by lambda 1. Lambda 2 is 400 nano, lambda 2 is 500 nano. Now it is 4 by 5, implies n is 4 and m is 5. I can take n by m equal to 4 by 5 as n is 4 and m is 5 only when least distance is mentioned. Okay, and it is mentioned. Second time, when will those two overlap? When n is 8, m is 10. Next time, n is 12, m is 15, isn't it? So we found the value of n and m. We have to find the distance. To find the distance, let us use this or this. Consider Xn equal to n lambda 1 capital D by small d. N is 4. Lambda 1 is 500 nano, 5 10 power minus 7. I have shifted the number of zeros, please take care. 1.5 by small d is 0.3 milli minus 3. This 1, this 5 times 5 5 25 into 4 is 100. 10 power 2 minus 7 minus 3 is minus 4. 10 power minus 4 equal to 10 power minus 2 meter. So Xn equal to 1 centimeter. So at a distance 1 centimeter, bright fringes of those two patterns overlap. Okay. Students, go through the problem, go through this explanation and solve this.